Okay, welcome back. This is the second part of our sound quality topic, and we're going to focus in on tonal noises and tonal metrics for working on tonal noises.
This sounds like a lot of mosquitoes. You already gave me the EBG. Oh my gosh.
Look at that, the big picture front and center there. Yeah, so tonal noises are characterized by distinct audible peaks at sort of limited frequency, usually one or some narrow band frequencies that stick up above the background. And it's sort of opposite of broadband noise where we have equal loudness at all of our frequencies. This is all of our energies concentrated at a few frequencies. And these tend to be very noticeable and usually more annoying than broadband noise. So like our mosquito example, yeah.
Broadband's like a waterfall. I don't think I quite did a waterfall there versus...
Sorry, you broke up a little bit there.
What?
Yeah, oh, can I hear the tone again? That was good. Yeah, you got it. I think if I looked under the audio dictionary of those two noises, I would hear those two sounds. So mosquito example, some other examples, electric motor, kind of makes some tonal noises, and often when we have pairing gears in a transmission or something, we can get a gear whine. Okay, so due to their unique nature, we need some specific metrics that are going to help us work on them. Now, one of the things that's important for tones, as we'll see throughout our time today, is we need to pay close attention to the amount of background noise. So if we're working on a tonal noise and we measure in this nice sophisticated lab where the environment's highly controlled and all the background noise is minimized, we're going to have a false impression of maybe how bad our tones are compared to how the machine will be used in the field or in operation. So if we're working on propeller noise, certainly in the lab we're going to have a different view of that and how the tones stick up above the background than we will when we're actually in flight. So it's important to always be sort of using these metrics with the appropriate level of background noise, right, Pete?
That's because the tone will meld into the background. You won't notice it, even if it's close enough to the background. Is that why?
Yeah, a lot of the stuff we're going to talk about today is just assessing, will I hear this tone above the background noise or not? So yeah, it's all about level compared to the background. Yep. So the first two metrics we're going to talk about are tone to noise and prominence ratio. And both of these are targeted basically at doing just what we talked about. Is this going to be an audible tone given the other noise that we're experiencing in the frequency spectrum? And sometimes we're trying to avoid that tone. Other times, in the case of alarms or things that are supposed to get our attention, we want to ensure that it's going to get our attention and it's going to be heard very, very audibly. So to opposite ends of the spectrum, we might use the same metric sort of for opposing purposes. And it's really assessing the tone's strength given the other noise that might be masking it, okay? So let's take a look at these two separately. Tone to noise ratio. Both of these metrics are standardized in the ECMA 74 standard. They describe how you do this calculation. And they're both aimed at deciding whether a tone is prominent or not, and that just means it's large enough in amplitude to stand out from the background, okay? And so tone to noise looks at the amplitude of the tone. So for this given band that we're analyzing right here, we would pull out the amplitude of the tone by itself, so this one spectral line, and then we would compare the amplitude of that tone to the amplitude of the noise energy in this band. And this is called a critical band, and it's just a group of frequencies centered around this main tonal frequency. And we look at the level of noise summed up across that band and see the difference between. So the difference between the tone's amplitude and how far it is above this critical band level, that is the tone to noise ratio. Okay, does that make sense, Pete?
Yeah.
So
how far out does it have to stick?
Well, we're going to talk about it because it's not a simple answer. But if it's prominent, then it's high enough above the background and it'll be perceivable. But as we'll see, this threshold is actually a function of frequency as dictated in the ECMA standard. And so when we say the tone to noise ratio is, for example, 9 dB, that is our how much above that level in the critical band that tone is. And so the tone to noise ratio is going to be 9 even if the overall level of that band is 100 dB or 50 dB. It's how big above that background band noise is the only thing we're really saying. Okay, so the tone to noise ratio is just the difference regardless of overall level.
Okay.
The other thing to keep in mind here is if there are multiple band tones in this band, so let's say there was another tone right here in the same critical band, tone to noise ratio is only going to look at the larger of those two. Okay, so it only considers one tone per critical band. This amplitude of this tone right next to it would actually get summed up as part of the background noise for that band. And so we might be a little bit misleading. We'll see how we can account for that. But so this is the threshold for prominence according to tone to noise ratio. So above 1,000 hertz, it flatlines at 8 dB. So if your tone is 8 dB above the level of that critical band, you'll get a prominence of yes, and you should be able to pull that tone out from the background noise. Below 1,000 hertz, that difference has to be bigger and bigger because we don't hear as well at low frequencies as we do at high frequencies like we've talked about. Okay?
Okay.
So its sort of sister metric is prominence ratio, and where tone to noise is like a tone to band comparison, this is a band to band comparison, also laid out in the ECMA standard. But in here, instead of looking at the amplitude of this tone by itself, we're actually comparing this critical band that contains the tone and comparing that to the level, average level of the two neighboring bands, as shown here in sort of pink. Okay.
Hey, Scott.
Yeah.
If you had that situation you mentioned before with multiple tones close together, then maybe this prominence ratio could help for that, because it'll take all the tones, obviously, in that band, not just the single tone.
That's exactly right. That's one of the benefits of prominence ratio. If you have closely spaced tones in your transmission or whatever you're working on, prominence ratio is probably going to match your perception better than tone to noise, because like Pete's saying, if there's a secondary tone right here, that would only add to this green level that's going to be compared to these neighboring bands and ultimately help us, call that tone or set of tones prominent. That's exactly right. So here we're comparing the level of the green band to the average of the sort of red bands here, and that's called our prominence ratio. Again, the prominence ratio, if we give it a certain value like 9 dB, it's just the difference between the bands. It doesn't have anything to do with absolute level. Again, it's set forth in the ECMA standard, but really this is that point we just talked about. If multiple tones are in the same critical band, both of these tones will be considered and they will raise the level of that band. Now this animation here is showing you that, in Test Lab, you put a cursor on there, you can calculate the prominence ratio for that cursor position. And you see that it's really about the band level and the neighboring band levels. And as we slide that cursor to the right, this background noise over here either is or is not included in this masking noise band on the upper end of the frequency spectrum. And so our prominence ratio actually goes down a little bit as this noise gets included, because it's the difference between this green band and the average of the red bands. Okay. So in Test Lab, there are some nuances on how the prominence ratio you're looking at is calculated. If you just calculate it in the legend, it's always the maximum, and you have to kind of look around in the spectrum for where that maximum occurs. If you do it for a cursor position, it's specific to that cursor position, and maybe we'll show you that in the software. Like tone to noise ratio, prominence ratio threshold for prominence is also a function of frequency. Cutoff is 1,000 hertz, and they use 9 dB for prominence ratio as opposed to 8 dB for tone to noise. But similar sort of trend for lower in frequency, that threshold has to be greater. Okay. One of the neat things about this is this tone to noise and prominence ratio actually works in what we call active picture. So you see I brought PowerPoint over here. And if I double click on this active picture, which is a plot I made in Test Lab, I can actually open it up right here in PowerPoint and then interact with the data as if I were in Test Lab when I don't really need a license of Test Lab to do that. And so you see, I can grab this cursor and I can add some calculations. If I right click on that cursor, I can do some calculations. And I've got prominence ratio and tone to noise ratio clicked on here. I've also got these prominence functions turned on, and that's this yes, no thing that you see up here. So prominence ratio, prominent, yes or no, then it tells me what the prominence ratio is. Same thing for tone to noise ratio and whether or not it's prominent. So if you remember, we went out to this peak.
I like that feature in the cursors, that PR prominent, and that way I don't have to know if it's 8 or 9 dB above or whatever. It's just yes, according to the standard you'll hear it, or no, you won't.
That's right.
Yep. I'm all set for management. You don't have to think.
Yeah. If we just color code them red or green, we'd be all set.
Okay.
So if you remember, this is a vacuum cleaner A if you remember from our last section. So you remember this middle tone here. We did not get any loudness improvement when we filtered this out. In fact, both tone to noise ratio and prominence ratio tell you no one can hear this tone anyway, so don't bother working on it. Same conclusion we got last time, right? But if I come down here, prominence ratio actually says yes, it's prominent, it's 12.81 dB above the background of the neighboring bands. Tone to noise ratio does not say it's prominent, and I would suggest it's probably because there are other tones right next to it in this critical band, and so maybe prominence ratio, tone to noise ratio isn't getting enough of a difference. You see it's 7.6. It's right on the hairy edge of that 8 dB.
Yeah.
Okay.
But yeah, that's a good point about the neighboring things.
Yep. So that's available to you in Test Lab as well. Here's a question for you, Pete. Prominence ratio application for you. I've got two vehicle run-ups, vehicle A and vehicle B. And both of these vehicles have some tonal things going on. And I want you to say, based on what you see here, which do you think is a bigger problem that I should work on first? So you see vehicle A, you see these tones here, 55, 60 dB in terms of sound pressure level. They come and go. So is this a bigger problem, or are these tones over here a bigger problem? And you see these are, 20 dB, maybe this one's 30 dB, whereas the rest of the background noise here going on is, 55, 60 dB. Which do you think is the bigger problem? High amplitude tones that come and go, or low amplitude tones that are kind of always there?
Well, I don't know if they're always there, right? Shouldn't we try some fancy metrics and some listening?
Yeah, I guess they always appear in the picture, right? So this would lead us to believe that they're there, but do we even hear them, right? I would tend to think vehicle A is the bigger problem just because we got 55, 60 dB tones coming and going, but can you help us figure it out?
Yeah, I can try. I think I processed it the way you suggested, so I changed the limits a little bit here. It's 50 dB just to make that tone stand out a little bit more.
Yeah, even better.
Yeah, so let's take a listen to these. Don't really hear the tones now. So they went. Now let's listen to brand B here. Yeah, I definitely heard tones throughout. I'd say brand B is probably more tonal than brand A. Would you say that too, Scott?
Oh, absolutely. Yep.
Yeah. So, like, if we were analyzing this, we might do something like, create some orders or something. Let me see if I can calculate some orders to prove brand A and brand B, which one's the worst. I'll hit OK here. And I can go in and I can add a processing cursor, an order cursor. And I'm going to make it a little bit wide. So line up over here. And I guess if I want, I can say coupled limits so that if I zoom in here, see this a little bit better, both sides show up. Processing. And I'll drop this in. And of course, I want to see that in dB. And I can do the same thing over here with the processing cursor. Maybe make that a little bit wider of a bandwidth. Drop it in. And line up on that really annoying tone. Uh-oh, Scott. Guess what?
What?
It looks like I didn't prove anything because these tones are lower in level, the absolute level.
Yep.
So maybe I should use that fancy metric you were talking about.
Yeah, you're basically just highlighting how decibel level can be misleading,
Right.
where a tool like Prominence Ratio might show us something a little bit more helpful.
All right, I'm going to try Prominence Ratio then and see if it's indeed more helpful. So I got a Prominence Ratio map of brand A here. And then I'll add another color map to this display. And I'll throw in the Prominence Ratio map of B. And I guess these should also be put in dB. Is that right, Scott?
Yeah, and really we don't care about anything below 0 because it's
All right. 0 to
dB
like
above the background.
8 dB above the background or something is where these things might show something.
Yeah.
All right. So, well, that shows something pretty different. Shows that this thing is a dominant tone throughout. In fact, this one is not even contributing in brand B.
Yep.
Maybe I'll try those order cuts.
Yeah.
And I'll already set this. I guess we know that in advance, 0 to, I don't know, 30 dB or something. So I'll do, I'll switch the axes to RPM. And then we can do order cut off of the map here. And this is going to be a prominence ratio order cut. So it's going to show me how many dB above the background my order is coming in, right?
Yep.
Let's take a look here. On the coming and going tone. Oh yeah, there it is. Tone is going above the 8 dB or so. So it's,
Yeah.
yeah, we hear that as a tone. Let's see how much above the background this tone is, huh? Ooh, that's quite a bit above the background there, Scott. So, yeah, I'd say prominence ratio and a prominence ratio map and order cut all make sense to me from a metric point of view. Hopefully that made some sense, Scott.
Yeah. It's the magic of the Prominence Ratio map.
Yeah.
So summarizing Prominence Ratio and Tone to Noise Ratio, both are expressed in decibels above the background. Okay, very critical like we just saw. These are specified in the ECMA 74 standard. And again, you want to make sure you have the appropriate amount of background noise present in your recordings before you use one of these metrics. Okay, check out the community for more reading. And then finally, we're going to talk about tonality. And there are a couple different formulations. There's DIN tonality, as described in 45681, and it is a method of essentially looking at a frequency spectrum and trying to identify if there are tones present, and if so, how sort of strong are those tones. And so if I click on this guy, it'll kind of show you how it goes through, how the algorithm goes through the frequency spectrum, and it's looking for a tone that is bigger than its neighbors, but then more than 7 dB above its second and third neighbors. And so that guy right there shown in green would contribute to the tonality calculation. Okay, so I'll show you this real quickly in the software. And so what I've got here is a recording, and it starts out where it's just broadband noise here in this beginning section. Then I add some tones to that broadband noise for this middle section, and then the broadband noise falls away and it's just pure tones out here. And what I'm going to do is I'm going to show you the tonality calculation. So we use this tonality unit, or TU, shown here, and essentially 0 tonality units is what we should see in that beginning section where it's just broadband noise, there are no tones. When it's a mix, we should get some tonality unit value intermediate, and then when the broadband noise falls away and we just have tones, we should get a tonality unit of 1. Okay, so we'll check out this tonality unit calculation as I play it for you right here. So 0, about half, and then just 1 when there is no broadband noise and just tones. Okay, so pretty straightforward. The DIN tonality is really just trying to give us an idea if we have tones in our spectrum, and then how prominent or strong they are in terms of our perception. Okay, so 0, no tonal components. 1, almost exclusively tonal components, or the tonal components are so strong and loud that that's all that really matters. Okay. So this is done on spectral analysis line by line in our spectrum, and it does not really scale with loudness. Okay. Now, there have been some extensions in the tonality world. Most recently, there has been this psychoacoustic tonality, which is based on a hearing model. Okay, and so you'll see it abbreviated tonality HMS. This is laid out again in that ECMA 74 standard, but it has 2 annexes, F and G. F lays out this hearing model, analytical hearing model, and then G is specifically about calculating new levels or units of tonality. And we see this new unit is given this TU with the subscript HMS, telling us it's based on the hearing model. Okay. The hearing model really is its whole purpose in life is to accurately model how human beings hear. So we've talked about A weighting a little bit. We talked about tones of curves of equal loudness. Hearing model does the same thing for perceptibility of tones. Okay. So some threshold values you want to familiarize yourself with this TU-HMS. 0.1 TU-HMS is where the tone should be barely noticeable. Maybe if you're an unexperienced listener, you may not hear a tone there at all. 0.4 TU-HMS is where a tone will be noticeable and will start to become objectionable. Okay, so it's sort of a go, no go. And then 0.8 is where you have an obvious tonal problem and it really becomes problematic. Okay, so keep those threshold values in the back of your mind as we talk. But one of the cool things about the hearing model tonality is that it scales with loudness. So as a tone or a signal gets louder to us, our perceptibility of tonality actually goes up. And louder signal with the same tones to background ratio will appear more tonal to us than a quiet signal. So I show you this same sort of combination signal that we just played in test lab, where it's broadband, mix of broadband and tones, and then just tones. You see the red function calculates a psychoacoustic tonality shown in red here. And then for the green, I cut the loudness in half. I literally multiplied all the values by 0.5, so the amplitude comes down. Psychoacoustic tonality actually calculates fewer tonality units, HMS, as would sort of track with our perception, okay? So nice thing is it models our human hearing and specifically about our perceptibility to tonal noises.
So this is kind of like the Ore's sharpness, takes into account the tonal characteristics plus the level, the loudness.
That's right. Yep.
All right.
So let's take a look at a couple examples in Test Lab. So I've got a pump here, and I'm going to play a recording for you, and I want to see if you think that there are any tones in this data here. So I've plotted time varying loudness here, but among the other things that I can process in here in Test Lab are all of these new psychoacoustic tonality metrics. So if I came over here and like I was having Pete do, I just start typing the word tonality in here, and you see I've got tonality, tonality frequency, and tonality map. And what I can do is tonality versus time is one of the ways to formulate this tonality metric, but I can also do tonality versus frequency, which will be more like a bark band versus tonality. Figure out which bark bands contain the tonality in my signal to help me maybe address that tonal problem. Tonality versus time is just going to say how many tonal units is my maximum tonality value versus time. And then tonality frequency is going to show me versus tracking parameter, time or RPM or whatever, which frequency that tonal problem is occurring at. Tonality map is going to kind of bring all of those things together. And so if I go back over here, I'm going to show you some of these results for that pump we just listened to. And if we look at the spectrum map, so this is just sound pressure level versus frequency, we see we have some tones down here, but we don't necessarily know if any of these are a problem or how big a problem that they might be. I could certainly try tone to noise ratio or prominence ratio, but I'm going to show you the power of tonality here. So tonality versus time is going to plot TU-HMS versus time, and you see the maximum value on this y-axis is 3. So 0.8 was when we had a serious tonality problem. I'm going to play this for you again and see if you can perceive specifically right here. These 3 and then this guy right here is where the tonality peaks out, and see if you can pick up what it's finding there. Did you hear that, Pete? Great. So I can hear it. I've heard this several times. Yeah?
Yeah, I heard it.
Great, great. So the tonality map will help us figure out, okay, what is making this peak in tonality. So it's going to plot tonality versus bark band or frequency. And you can see, I'll play this again once more for you, but this is that thing. Those are those 3 peaks right in a row, and then this guy is the really offensive one to me. See if you can hear that guy. Okay, and so the tonality map is plotting tonality units HMS versus frequency versus time, and I can see that really irritating tone in there is happening at about 1900 hertz. Okay, so I can go then back to my pump, figure out which components on my pump are making that frequency, and maybe address the problem that way. Okay, so this new psychoacoustic tonality will help me identify problems that are truly problems in a very objective way, specific to tonal problems and our perceptibility of them. So hearing model tonality, remember 0.1, 0.4, and 0.8 are sort of the threshold values you want to keep in mind. Again, it's laid out in NXG of ECMA 74, and we've got a whole article out there just on this tonality. You can go listen to a bunch more samples and abuse your ears, some tonal noises out there. So those are the tonal metrics. Pete, any wrapping up comments?
Thank you for not playing too many mosquito noises, Scott, and was very educational as always.
My pleasure.